Hi everyone and welcome back to my channel in Economist. So in today's session we will be learning a couple of things. We will start with something called the monotonic functions. We will solve a couple of questions on that and then we will gradually move to the concept of concavity and convexity. So let me start with this. What are monotonic functions? A function f is called monotonically increasing. A function f will be called monotonically increasing function if this particular condition holds. It says if x1 is less than equals to x2, that will imply if x1 is less than equals to fx2. Let us understand this graph. Here you see that x1 is less than x2, strictly less than x2. And if you draw the functional value, this is the functional value corresponding to x1 and this is the functional value corresponding to x2. You can clearly see that if x1 is less than fx2. So this condition is holding perfectly. So here this f is called monotonically increasing function. So it basically says that as your value in the domain, the x value in the domain increases, your functional value will also gradually increase, right? If your x value increases in the domain, your functional value will also keep on increasing in case of monotonic functions or monotonically increasing functions, right? And if you have strict inequality here, it is called strictly monotonically increasing function. I hope this is understood. Similarly, you have monotonically decreasing function where the opposite is true, that if x1 is less than equals to x2, fx1 will be greater than equals to fx2. So your domain value increases but your functional value goes down. That is what is the monotonically decreasing function. So here the slope is continuously increasing at an increasing rate. If you keep on drawing tangents, you will understand that here the slope increases at an increasing rate, but here the slope decreases at a decreasing rate. So this is the function and here this is the function. They are the monotonic functions. Monotonic means either it is keep on increasing either or it is keep on decreasing. And if you have strict inequality here, then you will say it is a strictly monotonically decreasing function. I hope this concept is clear. It's pretty simple. Now how to check a function is monotonic or not, right? So for that, let us take some differentiable functions. This is an important thing. The function has to be differentiable first, and how to check differentiability I have explained in my video. If you haven't watched that, I will give the link in the description. Okay, now let's see this. F will be called monotonically increasing, which implies that f prime x is greater than equals to 0. So it is nothing but the slope. F prime x is nothing but the slope of the function, which I was telling you that you can check monotonicity in terms of the slope. So keep on drawing tangents at every point and then it will give you the idea that the function is either increasing or it is decreasing. So if f prime x is always greater equals to 0 for all the values of x in the domain of the function, we will say it is monotonically increasing function. Similarly, if it is f prime x is less than or equals to 0, then the slope is decreasing or it is not going up at least. So for all x belongs to the domain of the function, you will say that the function is monotonically decreasing. Okay. Now for strict monotonicity, you will have strict inequalities here, nothing else, right? Let's see an example. Suppose you have a function f which is ln x. So your function fx is simply ln x. And the domain, what is the domain? Domain is from 0 to infinity. Right? Here you have this domain and you need to check if it is strictly monotonically increasing or it is monotonically increasing or decreasing, right? So this is what you need to check. So pretty simply you have to find out the slope of the function, that is the first derivative. F prime x, first derivative will give you the slope of the function, and if you do that you will get 1 upon x, which is strictly greater than 0 for all x greater than 0, and this is the domain. So you have to check in the domain of the function. This is the domain, and in this particular domain the first derivative is strictly positive, so it is strictly monotonically increasing function. Okay. Now we have something called the concept of locally monotone function. What is locally monotone function? A function if is called monotonically increasing in some interval and monotonically decreasing in some other interval. So locally means that in some particular range or in some particular domain, the function is increasing, and in some other particular domain, the function is decreasing. So in the entire domain, the function does not look like this. Either it is increasing or it is completely decreasing. This is not happening. So in some particular interval, it is always increasing, and in some other particular interval, it is always decreasing. If you have this in the domain of the function together, then you will say the function is locally monotone function. Okay, let's see an example. It says in which region the function, this is a polynomial function of degree 3 as you can see, and you need to find in which interval it is monotonically increasing and in which interval it is monotonically decreasing. So the first step would be always to find out f prime x, that is the slope. Let's do that. What will this be? 6x squared minus 24x plus 18. This is the slope of the function, just the derivative. I have shown you how to find out derivative in the previous lecture also. Right now what you have to do, you have to first equate this to 0 to find out the roots of this particular equation, or you have to see the 0 values where the function has the 0 slopes, right? So let me do that. X square minus this, so simplify. 3x minus x plus 3 0, so x minus 3 minus x minus 3 is 0. So x minus 1 into x minus 3 is 0. So from here what you see is that this slope gets 0 at two different points. First point is x1 equals to 1 and the second point is 3, right? So 1 and 3, the value is 0. And now how do you check that in which interval it increases and in which interval it decreases? For that we have to use something called the wavy curve method. We will use something called the wavy curve method. Let me show you how to do that. So here you have the real number line. It varies from minus infinity to plus infinity. Now here you have 0. Simply what you have to do, plot the roots here. So you have 1 and you have suppose 3 here, and then draw the function or the slope of the function here. What you have to do here, this is the slope that we are plotting, right? So it will be something like this. It will pass from here and it will go to here, and this will be f prime x. How do I know that this function will look like this? So at these 2 points the slope is 0, that we have already found out. And then the other parts how you can check is that it is according to the wavy curve method, that whatever roots you get here, right? You have two roots, 1 and 3. Take this root, start from this root, and you will always have positive value of the function after this point. So if you consider this region, you will always have a positive value. So after that I have drawn this thing, right? Now in between these two roots, you will always have a negative value of the function. So the curve is here, down below the real number line, which implies the slope is negative. And again, on the left hand portion of this point, you will always have a plus sign. And here the function will look like this. And this is applicable for any function you take. So just find out the first derivative, equate it to 0, and find out the roots at which this slope is 0. And once you have that, you can plot it in this real number line and check this, right? And you can also do for this, you can also, if you want to find out the root of any function in general, if you want to find out root of any function, you can apply the same method. In that case, here you will have 3 roots. It's a cubic function, so you will have 3 roots. And then also you have to plot this. Suppose here you have minus 1 is another root, so nothing happens, so it will just pass through here at this point like this, right? So in case of original function, if you want to find out the roots, then also you can apply this method. As of now, you don't need this. Okay. Now what you can say is that you have to find out in which interval the function is monotonically increasing and in which interval the function is monotonically decreasing. So for monotonic increase, you have to find out this region, in which region it is greater or equals to 0. Then you can simply do that from this graph. So you see that from the point 2, so 0 is also applicable. So the region will be from 3 to infinity on this side, and here what you have from minus infinity to 1. Or you can write it, you should write the left hand side first. So it starts from minus infinity. So from minus infinity to 1, the functional value is greater or equals to 0, right? At 1, it is exactly 0, and for the rest of the part, it is greater than 0. Union, you will start from 3 again, and you go to infinity. So this is the interval in which, or it is the domain in which this function is monotonically increasing. Now, in which interval it is decreasing, it is simply from 1 to 3, right? 0 is not here, so it will be open brackets. I hope this is understood. This is a very important approach, and this is very useful in finding the domain and range of the function. Also, you can find out the roots of any function using this method. Also, it is helpful here for checking the monotonic increase or decrease of a function. I hope this is understood. If you have any doubts, you can let me know. Okay. Now next we will move on to what is a convex set. Let's see the definition here. A set D, which is a subset of Rn, n-dimensional real space, is called convex if for any 2 points xy belongs to D. Now if you take xy from this domain, from this set D, which is a subset of Rn, it means that every point has n number of components. So these are not just singular points, these are all vectors. So x will take this form, x1, x2 up to xn, right? Since it belongs to Rn. Similarly, y will also have this kind of format, y1, y2 up to yn, and that will be belonging to Rn, right? So xy are vectors here which belongs to the set D, which is a subset of Rn. Okay, now the straight line segment between these points also belongs to x and y. So let us see graphically what it is saying. Suppose you have this kind of a set, this is set D, and you consider any 2 points, and this is a subset of Rn, so you don't need to visualize that. You are just visualizing it in a 2-dimensional plane as of now. So suppose you have this point x here and you have this point y here, and you join this with the line segment. You join these 2 points using a line segment. Then if this line segment entirely lies within this set D, then you will say that this is a convex set. D is a convex set. Similarly, for all this diagram, if you see, you join any 2 points anywhere, here, 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 here. So any 2 points within this set, and if you join this by a line segment, that line segment will be entirely in this set. Similarly for here. But if you, so all these sets are convex sets, right? But graphically, if you see, here there is a hollow here, right? So if you take 2 points here, I take this. Suppose you have x here and you have y here, and you join this with a line segment, then this portion will not be in the set, right? This portion is outside of the set. So this is not a convex function. Similarly, here you have this portion left outside the set. It is not a convex function, and here also. So if you have a hollow kind of a shape or this kind of a shape, then you will see this will not be a convex function. Now let us understand mathematically what it is saying. See this expression. I hope you know from your high school that this is the convex combination or the linear combination of 2 points x and y. So here h is a fraction lying between 0 and 1. So any line segment, you have x and y, and if you join this with a line segment, then any points here right? Any points here or this line segment itself can be represented in this particular format, where h belongs to 0 to 1. It's a fractional quantity. And this is also known as the linear combination or the convex combination of 2 points. So that is what the definition says, that if this linear combination, so this line segment basically also belongs to set D. So you said that x and y, they are 2 points which belongs to set D. If it implies that this linear combination also belongs to set D, you will say the function is convex, otherwise it is not convex. Okay. And here you have a very important theorem on this. I haven't given you the proof, but as of now just understand the theorem that let S1 to Sk be convex subsets of Rn. So you have this k number of convex subsets of Rn, then their intersection, if you take intersection of them, they will always be convex. So if you have set 1 here, set 2 here, set 3 here, in this way you have total k number of subsets. And if you take intersection, so this is the intersection portion of all these convex sets, then it says that this intersection will always be a convex set, right? But if you take union, this will need not be a convex set. So in some cases it might be convex, but it is not necessarily true. You can, for this portion, you can just give an example to prove this. You don't need to prove the entire thing, just give a contradictory example to show this. But this has a nice proof which I will be showing you in some other lectures. Okay. Now that we know what is a monotonic function and what is a convex set, we will move to the concept of concave and convex functions, right? So let me do that. This is the mathematical definition, and looking at this you might feel that it's very difficult, but once I explain you graphically you will see that it's not that complicated. So a function f is called convex in the domain D, which is a subset of Rn. Again, it is n dimensional, so every point you take from this set, it will be having n number of components. So it will be in the form x1, x2 up to xn. Simply this is the concept of Rn. So D will be called convex. This will be convex if this condition holds. It says f of 1 minus h into x1 plus h x2. So this is the line segment, right? This is the line segment that we have discussed in the convex set concept. So if you take the functional value of that line segment, that will be less than equals to the linear combination of functional values. And for all x1, x2 belongs to D and all h belongs to 0, 1. And it will be concave if the reverse is true, greater than equals to. I think I should explain this with the help of an diagram that will be more clear to you. Suppose you have this. If I have to say in the layman term, how do you identify convex function and concave function? If you see, you have this function fx here, and you have this function fx here. This is the function, and if you take any 2 points on this function and join it by a straight line, and if you notice that the line, this line joining these 2 points is always above the function, if the line is greater than the curve or the function, then you will say this is a convex function, right? In a visual way, if you want to know. So the line, if the line segment joining any 2 points on the curve is always greater than the curve itself, then you will say it's a convex function. And the reverse is true for concave, the line will be always less than the curve. Now if you have to put it mathematically, then you have to apply this formula. Let me show you. This is x1. Suppose this is x, this is fx, right? This is x and this is fx, right? So you take any 2 points in the domain of the function. So x1, here you have 2 points in the domain x1 and x2. The functional value corresponding to x1 will be here. This is fx1, right? This is fx1. So you are putting the functional, the domain x1 here in the function. So you are getting this fx1. Corresponding to x2, it will be fx2. right? This is fx2. Now you are joining this line. Now if you understand the concept of convex set, I have told you any point here, any point in this segment, how can you write that point? That will be simply a linear combination of x1 and x2, right? So you can write it in this way: 1 minus h into x1 plus h into x2. This is the linear combination, and if you vary h, any point in this space can be written in this fashion, right? And here you have fx1, here you have fx2. So how will you write the points on this particular line? Any point, any point on this particular line can be expressed as this: 1 minus h into fx1 plus h into fx2. So this is the linear combination of fx1 and fx2. Here you are doing the linear combination of x1 and linear combination of x2. That is giving you this particular line segment, right? But here in this line segment, you are joining the points fx1 and fx2. So it will be linear combinations of fx1 and fx2, right? Now what is the identifying feature of convex function? If you now join it with a line segment, take any line segment here, what you will see, you will see that this point here is always greater than this point here, right? So this point here is always greater than this point here. And I have said that this point can be written in this form. Now how will you write this particular form? If you see, this is just the functional value. This point is just the functional value of this line segment. So it is 1 minus h into x1 plus h into x2, right? So previously what I have told you, that corresponding to x1 you have functional value fx1, corresponding to x2 you have functional value fx2. So corresponding to this point, which can be represented using this, so you have the functional value, just simply instead of x you are putting this line segment. So f of 1 minus h x1 plus h into x2. And if you compare, you will see this point is higher than this. So you will say this thing has to be greater or equals to this thing, f of 1 minus h into x1 plus h into x2. And that is what the definition says. This is the definition, that for a convex function, f of 1 minus h x1, that is the functional value of the linear combination, has to be less than equals to the linear combination of functional values. Let me explain it to you with the help of this concave function once more. Here you have a more clear picture. So I have told you that the identifying feature of concave function is that the curve is always above the line. From the first glance itself, you can identify this, that the curve, if you join this line segment, the curve is always above this line segment, right? So but just by looking at this function, you know that this is a concave function. But if you have to mathematically put it, you have to write it mathematically. So here you have x1, here you have x2 from the domain of this function. And again, so this segment can be written in this way: 1 minus hx1 plus hx2. So now if you want to know this point, this is this point, what will that be? It will be the linear combination of fx1 and linear combination of fx2. So this is the point here. You can see here 1 minus hfx1 plus hfx2. And from this point, if you draw this line segment, you know the functional value to be this, f of this. And you can pretty clearly compare that this is greater than equals to, right? So this value lies above this value. So this is a higher value, and this is what is the condition for a concave function. I hope graphically you understood these things. It's very simple if you know the logic behind it. And similarly, the concept of strictly concave and strictly convex function, if you have the strict inequalities, the logic is completely the same. These inequalities will be strict, nothing else. Now I have given you an example of a linear function, and I have shown you how you can check it is concave or convex, right? Or strictly concave or strictly convex. Let us go through this example. So you have this as the function, simple case. Since in semester 1 you have only single variable cases, so I haven't gone into multivariable case as of now. I have taken only one explanatory variable here. Okay, so just see this, fx is a plus bx. This is a simple linear function case. You take 2 points x1 and x2 from the domain of this function. Then simply calculate the left hand side and the right hand side. So f of 1 minus hx1 plus hx2. So instead of x, write this value. Here I have written this and I have simplified to get this expression. Similarly, find out this. So you are basically finding this expression and this expression separately, and then you will compare that it is greater than or less than. So if you do this, if you solve this, you will see this. And these two expressions are exactly equal. They are not greater than, they are not less than, they are exactly equal. So from that, what you can conclude is that linear function is both concave and convex. It's very important to understand this. Linear function, any linear function you take is always both concave and both convex. This is possible, right? This I have shown you here. You can take a screenshot or do it for yourself. And this is the workout. So you can look at this if you want to know in the vector form. This I have taken as simple example, and this is in the vector form. A is now R component vector. So A is in this form, A1, A2 up to AN. And now if you consider the function to be this, transpose means this, and x1, x2, xn. So if you take the transpose, no, I have just a minute. So what you are doing is that this x1 to xn. So if you take transpose, it will be a1, a2 in this way. You know the transpose of matrix, though I haven't covered matrix as of now, I will be doing that. And if you multiply, it will be a1 x1 plus a2 x2 plus an xn in this way, right? So this is also a linear function in the vector form. In the vector form, because every element is taken from Rn. So n-dimensional real number 3, right? So now the same thing you have to do f of 1 minus hx1 plus hx2. So instead of x, just write this, and if you simplify, you can simplify this in this way. Simple calculation. So you will again see that every linear function is both concave and convex. However, a linear function is neither strictly concave nor strictly convex, as the inequality is never strict. So here we have seen strict equality, but there is no possibility of strict inequality here. So it is both concave and convex, but it is neither strictly concave nor strictly convex. Similar thing you can do for checking quadratic function. So simple case again, fx is x square. Again take 2 points in the domain and check this condition f of 1 minus h into u1 plus hu2 and find this expression. Simply what you can do for your calculation, you can take subtraction. Subtract this from this, and here I have shown you the complete derivation. It's simple calculation. You have to just expand the square and take common things, and you will notice that this minus this expression will come out to be strictly less than 0. You can take a screenshot, you can do it for yourself. You will see this will be strictly negative. So this is negative for u1 not equals to u2. So the points has to be distinct. The points that you're taking from the domain has to be distinct points, and h has to be a fraction. Then we can say that this is showing that it is strictly convex function, right? So this expression fx is x square is a strictly convex function. In this way you can check. But if you see, this derivation is pretty big, right? This is the actual thing. You can take a look at this. This is the same thing. I have done, handwritten it for you. You can check. Now you have got certain properties, but if you see this derivation, you will see that they are very big. And for that, you have a simplifying method also. I will be showing you that. But first, let us go to the properties of convex and concave functions. So if fx is convex or it is strictly convex, then minus fx is concave or it is strictly concave. So if fx is convex, minus fx will be concave, right? This is what this is saying. And if you have strict, then here you will have strict, so nothing else. If x is convex, then minus fx will be concave, and vice versa. Again, if 1x, f2x up to fkx are convex or concave functions, alpha 1, alpha 2, alpha k greater than 0, then if you take a linear combination or a convex combination of this will also be convex or concave. So if you take multiple convex functions or multiple concave functions, and if you take linear combination of them, they will also be convex or concave. So this is also an important thing to remember. And finally, what it says is that if at least one of the functions, if ix here is strictly convex or strictly concave, then gx is also strictly convex or strictly concave. So suppose this expression, so you have k number of convex functions, and the first function, if 1x is strictly convex, then your entire linear combination will become strictly convex, and similar thing will happen for strictly concave. So these are some important properties of concave functions and convex function. Now let me introduce to you another simplified way to understand what is a convex function and what is a concave function. So every time you cannot find these huge expressions to check that the functions are convex or concave, so you have to apply some other rule. And since you are dealing with a single variable case, it's very simple to do that. Let's see, suppose you are taking 2 times differentiable function. This is a criteria, this is a prerequisite. You have to take a 2 times differentiable function in order to apply this method. Then f will be convex if the double derivative is greater or equals to 0 for every x in the domain, and it will be concave if it is less than equals to 0 for every x in the domain. And this is a very simple thing to do, and a very simple way of computing things and checking things. Now why it is so? Double derivative gives you the curvature of a function. So convexity concavity implies the curvature of the function. So either the curve is going like this, first it is concave, then it is convex, or first it is convex and then it is concave. So this change in the curvature of the function is given by the second derivative. Why is that? Because it is simply ddx of df dx, and df dx is the slope of the function, right? Df dx, so you are measuring the change in the slope of the function. So if you see from this example, what is this? This is, we have just discussed that this is a concave function. So here you will see initially the slope was this, then the slope gets flatter, then you have this maximum point, and then the slope again changes and it comes down, right? So it initially increases, you can see the slope initially increases, reaches a maximum, and then it comes down. So this change, the change in the curvature or the change in the slope, will be measured by this second derivative. So this expression is nothing but ddx of df dx, so which you also write as in this way, d2f dx2, right? d2f dx2. So this is nothing but ddx of the slope. So you are basically saying how the slope changes in terms of curvature. The change in the slope will be measured by the curvature, which is given by the second derivative. So if you see, for convex function, the change in the slope is greater than equals to 0. The slope changes in a increasing manner, in an increasing fashion. And for concave function, the slope increases at a decreasing fashion, right? Here you can see the slope increases at a decreasing fashion. So this is what you have as concave function rule, right? Now let us see these 4 cases. In this case, you have 4 possibilities. So we have already seen the first derivative will give you the monotonicity of the function. So you will know that the function is either increasing or decreasing, and is it strictly increasing or it is strictly decreasing. So that is given by the first derivative. And the second derivative will give you the curvature. The second derivative will give you curvature, and you have these 4 possibilities. If prime greater equals to 0, if double prime also greater than equals to 0. So the interpretation will be, f is increasing, this which is given by this, f is increasing at an increasing rate, because the double derivative is also positive. So double derivative is measuring the rate of change of the slope, right, which I have mentioned. So f is increasing and it is increasing at an increasing rate. Similarly, here you have f is decreasing at an increasing rate. Here you have f is increasing at a decreasing rate, and here you have f is decreasing at an increasing rate. Right? I hope this is clear. It's very simple. And if you consider only these two cases, this will give you convex functions, because the double derivative is positive. And if you see these two things, it will be concave functions, because the double derivative is negative, which we have just discussed here. Okay. And again, you have for strict concavity, strict convexity, these inequalities will be strict. Now let us quickly look at some examples. Example of convex function. This is a classic example. Simply find out the double derivatives. What is double derivative? It is as it is, which is strictly greater than 0 for all x, for all x which belongs to R. So it is a strictly convex function, right? This is a strictly convex function. Exponential function is strictly convex. Here you have the proof, and this is the graph of f(x). This is e to the power x. Graphically also you can see, take any 2 points here, and if you join it by a line segment, you will see that the line is always above the curve, right? Line is always above the curve, which implies that it is a convex function. And the second example is of concave function. F(x) is ln x. So again, you can simply do this. If double x will be minus 1 upon x squared, which is strictly negative for all x greater than 0. The domain is this, right? So for all x greater than 0, it is strictly negative. So it is a strictly concave function. Okay. And here again, if you take 2 points and if you join this, you will see that the curve is now above the line. Curve is above the line means it's a concave function. And here you have strict inequality, so it is strictly concave. Now you have something called the locally convex function, but I want to clarify this, that a function will be concave or convex in the entire domain. So in this entire domain, if the function is concave, then only you can say that the function is concave. In the entire domain, if the function is convex, you can say that the function is convex. But if this is the case, that the function is like this, in some particular range it is concave and in some particular range it is convex, then the conclusion would be the function is neither concave nor convex. So this is an important thing to remember, is that concavity and convexity will be on the entire domain of the function. And this is an important thing, you sometimes get questions on this, that concavity and convexity has to be on the entire domain. So why we are defining this locally convex functions? Because they are important to find something called the inflection point. So inflection point is a point that we will be coming in the optimization video later on. So inflection point is a point which will give you this break, in which the function either changes from concave to convex or it is changing from convex to concave, right? So that point will be given by the inflection point, but you can find out in which range it is concave and in which range it is convex. So locally convex, just as like monotonic, locally monotonic functions, we will see that if can be convex in some interval, it is concave in some other interval, and that will be locally convex. So for that, again, this is the way of finding this. Find out second derivative, determine all the roots, and then see in which interval it is greater than 0 and in which interval it is not. So here I have given you an example. This is also a cubic equation. So it says in which region it is concave. So you have to find the second derivative first and see in which region it is less than equals to 0. Here the roots, here you have only a single root, x equals to 1. So you can apply the wavy curve method again of minus infinity and infinity. Suppose this is 2. So what you know is that on the right hand side you will have positive, on the left hand side. So the function will be like this. It is negative first, then here it is 0, and then it is this. So here you have positive thing, here you have negative thing. So in which region the function will be concave? So find the region where this is less than 0. So it will be from minus infinity to 2, right? In this region the function is concave, and from 2 to infinity, it is convex, because if double prime is greater than 0, and here it is less than 0 if double prime. So this is the way of finding in which region it is concave and in which region it is convex. But actually this function is neither concave neither convex, because it is changing sign in the changing the curvature in its domain, right? So the actual conclusion is this function is neither concave neither convex, but just for the sake of the question you can apply this. Okay, now we have understood how to see concavity convexity mathematically using definition. We have also seen how to find it out using the double derivative. Now there is another way of doing this in terms of the quadratic form, and this is associated with the concept of matrix. I haven't covered matrix yet, but just for the sake of completion of this chapter I have given it in a brief way. I will be coming to this later on. Suppose you have a matrix A which is symmetric. Symmetric matrix means A transpose is A. I will be covering all this in detail later on. So you can say that any quadratic form corresponding to this matrix A can be written in this way: X transpose A into X. Let me show you this. I have written here why it is so. X transpose A into this. Suppose you are dealing with 2 cross 2 matrix. A is 2 cross 2. So you can find out in this way what will be the quadratic form. X1, X2. You have 2 cross 2 matrix here, A and this. If you simplify, this will be your quadratic form in terms of X1 and X2. So this is basically a quadratic form associated with matrix A, right? Now if you want to know that if this quadratic form is convex or concave, this is also something which comes in your exam. So if you want to know the quadratic equation corresponding to your matrix is concave or convex or not, then you have to apply certain rules. There are two ways of doing this. The first would be in terms of the eigenvalues. First will be in terms of eigenvalues. So simply find out the eigenvalue. I hope you know how to find eigenvalue. I will be also making video on this. But as of now, just understand that if you know how to find eigenvalues, and if you see all the eigenvalues are positive, strictly greater equals to 0, you will say that the quadratic form associated with matrix A is convex. If it is every eigenvalue is negative, less than or equals to 0, you will call it concave. And if you see that some eigenvalues are positive, some eigenvalues are negative, you will conclude that the function is neither convex nor concave. So this is also an important aspect of concavity and convexity. Okay, now this is the first way, and the second way would be in terms of the definiteness of the matrix. What is definiteness of a matrix? Let's see this chart first. That a function is strictly convex if it is positive definite, convex if it is positive semi-definite. In this way you have all these cases. You can take a screenshot. This will come very handy for your exam. Now what is the definiteness of a function? Here is the definiteness formula, that if A is a square matrix, symmetric square matrix, again A transpose is equals to A, and suppose delta I is the determinant of the leading principal submatrix, and I'll be showing you with an example what it is, then you will call A to be positive definite if this leading principal determinant is strictly positive for every I. It will be negative definite if this is positive for even i's and negative for odd i's. Indefinite if the determinant is not equals to 0, and if the determinant is 0, it is either positive or negative semi-definite. Let me show you with the help of an example. It's pretty simple. If you understand things mathematically, it becomes more clear to you. So I have given example to everything that I have been talking about. Okay, so let's see this. This is a 3 cross 3 matrix. A is a 3 cross 3 matrix, and you want to know the quadratic form corresponding to this matrix is concave or convex or what. For that you have to find out the leading principal minors. What are the leading principal minors? The first leading principal minor is simply this term. right? Simply this term. So here you have 2, which is you see strictly positive. The second leading principle will be determinant of this thing, 2 1 1 3, and if you take determinant it is 5, which is also strictly positive. And the third principal minor, leading principal minor, would be the entire 3 cross 3 matrix. If you take the determinant, you see this is also positive, and we have explained that if this is positive definite, every here positive definite, every leading principal minus determinant will be strictly greater than 0, and that is the case here. So the function is positive definite, and the quadratic form associated with this matrix A will be strictly convex, right? This is another way of doing concavity and convexity thing. Let us take another example. This is 3 cross 3 matrix. The first principal determinant is negative, as you can see. If you find the second principal minor, this minus 1 0 0 minus 4, this is positive, this is 4, this is positive. And if you take the determinant of the entire thing, which is this, it is 0. Now if you go back to the definition, if some determinant is 0, it is either positive or negative semi-definite thing. Now we have shown you that again from the definition, for negative definite this will be 0 for even terms and this will be negative for the odd terms, and this is what you see here, that for the odd thing, which is 1, the first leading principal minor is negative. For even term, the second principal minor is positive and the third principal minor is 0. So it is a negative semi-definite thing, right? Negative semi-definite. Matrix A is negative semi-definite, and if you go back to the chart, for negative semi-definite, the function is concave. So the conclusion will be that the quadratic form QA associated with this matrix is concave but not strictly concave. I hope you understood the process. I have covered in details what is concavity, convexity, and I have given you 3 approaches to find that out. Either you can find out graphically, you can use the definition, or you can use the double derivative, or you can use the definiteness of the matrix or the eigenvalue. So there are multiple ways of finding the concavity and convexity, right? Now we have a short final topic to be quasi convexity and quasi concavity, which is also a very simple topic. Let us understand the definition first, and with this I will wrap this session. So what is a quasi convex function? A function if is called quasi convex in D, which is a subset of Rn. If D is convex, so D is convex, and every lower level set is convex. What is a lower level set? This is the definition of a lower level set. So suppose you have a function like this. So this particular set is called the lower level set or the lower contour set. Lower contour set, right? And again, and this will be the upper contour set graphically, and mathematically you write in this way: all the x which belongs to the domain of the function for which fx is less than equals to c. And if you see this lower level set is convex, then you will say the function is quasi convex, right? So you have a function like this, you find out the lower level set or lower contour set of this function. If you see that this lower set is convex function and convex set, so I have already told you what is a convex set. So you take any 2 points here and join, you will see that the line segment lies entirely here, right? So this is the convex set and the function will be quasi convex. Similarly, for quasi concave function, D is convex, this is as it is, but the upper level set, the upper contour set will be convex. Let me show you this with the help of an example first, then I'll be going into some other thing. Okay, this, let's see this, how to graphically see that a function is quasi convex or a function is quasi concave, right? Let's look at this diagram. You have x as the domain and fx is your function. You take 2 points in the domain x2 and x1. This is your function. Now you have to know if it is a quasi convex function or a quasi concave function. How will you check that? First, find out the functional value. This is the functional value fx2. This is the functional value fx1. Now the definition says that if this functional value of this expression, functional value of this is strictly less than equals to max of fx1 fx2. So what is the max value here? Max value is fx1 here. So it says if the entire function lies below this, if the entire function lies below this max value, which is fx1 here, the function is quasi-convex. Let me again repeat that for you. How to check graphically a function is quasi-concave or quasi-convex or not. Find out max value of fx1 fx2. Here if you see, fx1 is the max value, right? So this is the line segment, green. In green you have this line segment denoting the functional value fx1. So if your function, and this is the linear combination which I have been talking about. If you take functional value of this linear function, suppose this is the functional value, f of 1 minus h into x1 plus h into x2, right? If you see this functional value, this can be here, this can be here, this can be anywhere here. So if you see, every functional value in this format is strictly less than equals to max of this, which is x1 here. It is a quasi-convex function. So this function is quasi-convex. If you have any doubt, you can let me know. And for quasi-concave, the opposite is true. You have to see this value is greater than equals to minimum of this. This is the criteria that we use to find out quasi-concavity and quasi-convexity. So minimum of fx1 fx2 is what? Here fx1 is this point and fx2 is this point. So you have to check in terms of fx2. This is fx2, and you see that every value here is greater than, the function entirely lies above this fx2, right? If you only considering this portion, this segment from x1 to x2, the entire function lies above this fx2 level. So this is quasi-concave. This is quasi-concave, right? Okay. Now, what is the relationship between the concavity and quasi-concavity, or convexity quasi-convexity? This is very important thing which you have to know, that every concave or convex function is also quasi-concave or quasi-convex function respectively. This is very important, that every concave function, this is one of the ways of identifying quasi-concavity, quasi-convexity, that every concave function is also quasi-concave, every convex function is also quasi-convex, right? This is something you have to remember. However, a quasi-concave function need not to be concave, right? However, a quasi-concave function or a quasi-convex function need not to be concave or or convex, right? So what I am saying is that every concave function is quasi-concave, or every convex function is quasi-convex, but the reverse is not true. Reverse is not true. Every quasi-concave function is not concave function, every quasi-convex function is not convex function, right? So basically quasi-convexity is a weaker condition that we will understand in a while. This is a weaker condition. Every convex concave function is quasi-convex, quasi-concave, but the reverse is not true. And here you have a property that if t be strictly monotonically increasing function, and f is convex or concave, then if you take composite function t of f, it is also quasi-concave or quasi-convex respectively. And this example here involves two variables which I haven't discussed yet, so but you can take a look at this, that this function is quasi-concave, the function is this is concave. Then if you take a composite function that strictly monotonically increasing, but this will not be concave. If you understand these things, it's good, but it is not necessary for now. Now see the weaker condition, why we are saying it's a weaker condition. The notion of quasi-convex is weaker than that of the convex, in the sense that every convex function is also quasi-convex, but not vice versa, which we have discussed. And there are much more quasi-concave or quasi-convex functions than the convex ones. What is the importance? What is the importance? The importance of such weaker notion is based on the observation that a couple of propositions still holds if convex is replaced by quasi-convex. So suppose you have a theorem which is established using convexity. But if you replace the convexity by quasi convexity, then also the theorem holds good. So these are the important things to remember, that this is the importance, that if you replace also, then also some of the theorems still hold true. So that is important. So if you know that a function is quasi convex, then also you can establish a theorem. You don't need to know the convexity property. In this way, we get a generalization of a theorem where a stronger condition is replaced by a weaker one, right? Okay. And for strict convexity, strict quasi convexity concavity, you have the strict inequalities here. Condition is same. And finally, we will wrap up using two examples. So this is exponential function. We have previously proved that this is strictly convex function. So by definition, we know that this is also quasi convex function. But just to show you how to do this and how to find the domain in which this function is quasi convex. So let's see this. Okay, let me go to the definition. For quasi convex, the lower level set, this is the lower level set, this set has to be convex. So let's see, x belongs to the domain of the function such that if x is less than equals to c, right? This is the definition. This is the definition. Now if you replace fx by e to the power x, you will see less than equals to c. Now if you take log here, x ln e is less than equals to log c. ln e is 1, so x is less than equals to log c. So this is the domain in which you can calculate the quasi concavity or quasi convexity. So here, if x is a strictly convex function, that implies it is strictly quasi convex. Yeah, it is strictly quasi convex. And what is the domain for that? The domain is x is less than equals to ln c. So in this particular set, you will see that the lower contour set means it is this portion, right? This is fx is e to the power x. So this is the lower contour set of the lower level set, whatever you want to call it. This set will always be a convex set, because if you join any 2 points with a line segment, this will be entirely in this set. So this entire set below is a convex set, which basically implies that it is a quasi convex function, right? So using definition you can do this, or you can simply plot this diagram and check for yourself what is the case. And in this way you can find a domain in which you can check the quasi concavity and quasi convexity. Finally, you have this example where you know that logarithmic function is strictly concave. So by definition you know that it is strictly quasi concave, right? It is strictly quasi concave. But just to know the domain for okay, let me go to the definition once. Yeah, this is the definition. So upper level set has to be convex, right? This is the definition of the upper level set. Let me go here and show you, such that if x is greater equals to c, so replace fx by ln x has to be greater equals to c. If you take exponential both sides, so e to the power ln x greater than e to the power c, so it will be simply x e to the power ln x is x greater than e to the power c. So if you consider this particular domain, then you can show that it is a strictly concave function. Why is so? Because the upper contour set, this is the upper contour set of this function, right? This is ln x, this is the upper contour set of ln x. So everything over and above this function, and this set is convex. You can show that if you join any 2 points, this will be entirely in this set itself, and it will be a convex set. Since the upper level set or the upper contour set is a convex set, the function itself is strictly quasi concave. And with this I complete everything that you need to know about concavity, convexity, quasi concavity, quasi convexity. I have also covered in details what is a monotonic function. And I hope you find this video helpful. If you have any questions, any doubts, you can let me know. And thank you for watching this video, and I am putting in a lot of effort in making the slides and explaining things to you. So if you like my video, then give me a thumbs up, and don't forget to subscribe to my channel for further videos. In the next video, I will be covering the single variable optimization, so stay tuned for that. And thank you for your time.